Okay, so good morning. I actually just prepared some words on the student's question who is not here yet.
He's coming.
He's coming. Okay, I just want to make a comment on your question from yesterday. So it's good that you know. So you were asking why, for example, for 6 points amplitudes, I consider these diagrams and not for example diagrams with a 4-point vertex like this. And of course, clearly, when you just count dimension of the same dimensions, here you have 3 propagators, you have 3, and then you have here final vertices, which is, I mean, let's write it like xi1, xi2, and then xi intermediate with k1 minus k2. This is a polarization. I also just put prominent there. So each vertex here, each 3 vertex comes with order of 3, so you get k to the 4. So in total this is 2 to the 4, 2 to the 6, which is 1 over k squared. Of course, all field theory diagrams have this dimension, also this guy, because here now you have only kind of two propagators, only two Feynman vertices and 1 4 vertex, which is dimension, which doesn't imply a k. So in this case, with the k4 it has the same dimension. So why did I not consider this diagram? Because this you can of course always write like s k squared to the s to the 3. So you can always shuffle those contribution of this diagrams to this such a contribution, but I made this how to get this power or this denominator from the virtual integrals, and so the typical setup is that I have a virtual integral times some kinematics n. So the n is, for example, contained all this stuff from here. So with such an object from this, I want to get this s over 3. Then I can put everything else coming from 4-point vertices into the n by doing this extension. Okay. So I trade these diagrams into essentially as those diagrams by extending, by also writing it with 3 propagators. And this actually will be done in the following when we talk about BCJ numerators. So we have derived from string theory, from string amplitudes. We have obtained nice field theory relation, namely for 4-point. So we'll first discuss 4-point and 5-point. So we have found these Klein-Kolb relations from string theory, which then gave us also relations for field theory, namely so Young's amplitudes. This color order Young's amplitudes fulfill certain properties. When you permute, for example, the 2, so on this object. So this is you all know. And then we got this BCJ relations, which these relations are also called real part relations from the string monotony relations, and this was the imaginary part relations. It was taken alpha prime to 0. And extract the field theory relation. So there, the BCJ relations was a 4-point amplitude read like that. And my Mandelstands are as usual. So I mean, P is in my case K1 was K3 squared, and the rest is further definition. So what Bernd Carrasco-Johansson did in 2004 is that they made an ansatz, let's say an educated guess of all these amplitudes, how they might look like with respect to such a propagator expansion. So let's first look at this color order amplitude. Of course, when you compute in field theory with the Feynman diagrams, these diagrams are now that you might have a S-pole. So these are precisely two diagrams we need to consider, which were computed before by this polygon division problem from yesterday. So the Catalan number equals 2. So these two diagrams can only contribute to here, and of course there's also a 4 vertex, which is dimensionless. So here you have propagator 1 over u, 1 over s. So we can make the following ansatz. So this is ansatz by Bernd Carrasco-Johansson. So so when we compute it, this, for example, this diagram, then we have of course to take into account our Feynman rules. So we need this Young-Mills 3 vertex, and we have to combine it with another 3 vertex from here in the propagator, and this will give us something which we don't specify further, which is called numerator ns, and similar for nu. And now, according to this line, so I showed you at the beginning, is anything from this guy doesn't have a numerator, a denominator, so we can always put it somewhere to here, or divide it up, break it up, and put a piece here and put a piece there. So that's completely obvious. Now we can write down the other amplitudes. So this amplitude has a t-pole, 1, 3. So clearly has a t-pole, and it also has a s-pole because this and that guy that you should be aligned along the cycle. So this is 1 and 2. So now comes but so here when we compute here the S pole contribution, it turns out, I mean, it's kind of obvious that we get the same numerator, but actually we get it with a minus sign. So I will explain this to you in a moment, why we have this sign flip here. So we don't get any new numerator from the S pole, because we get just this numerator with a sign flip. I will in a moment tell you why this is like that. And similar for this diagram. Of course, in this diagram we have the U pole contributed as a P pole, sorry. Let's write it like that. So the first and the third come together, and then you have this exchange, T-pole exchange to 2 and 4. Okay, and then again the S chain. And so why do we have the sign flip? Why do we have the sign flip? So assume, so let's just sketch how we compute this numerators by putting together the Feynman the two Feynman 3 vertices. So in the first case, when we compute this, we have this diagram, and actually by applying this, we get something like NS is something like 7, say 2, K1 minus K2. This is from the two incoming clones, and then from this one we have K3, K4, K3, K4. So xi are the polarization of the clones, and this is constructed with a propagator. With the propagator here is g mu over s squared over s. So that is what I mean. But the s is when we have the s extra. So this is what you would compute, right? And now, however, now for this numerator, but now we compute this diagram, and of course we have again a propagator in S, because we have 1, 2 here. So now you see already, because I have exchanged this 2, I have to exchange here 3 and 4. So that is precisely where the side flip comes from. I have to exchange 3 and 4, and otherwise I get exactly the same numerator. So here I get minus ns, and that is why we have this minus ns here. And similar for the other cases. So now we can see one. We can see one. We clearly see that with this 3 amplitudes, this KK relation is trivially satisfied. So you see that, I mean, that means this was already a quite educated guess to write it like that, because of course if we would have written now something in addition here, accounting for the 4 vertex, then this wouldn't be so fulfilled anymore. So the KK relations are trivially satisfied by this answer. So this, of course, tells us that we have actually only 2 independent amplitudes, which you clearly see from this numerator. You can always, by this relation, express the third one by the other 2. And a new or non-trivial impact comes only from BCJ relations. So it would have been completely enough just to write down these 2 amplitudes, I mean n minus 2 factorial, and focus on the BCJ relations only. So and I recall the ansatz can be always achieved also for a higher point, as we will see, by absorbing the contact terms into the numerator. So let me stress this. Now, I mean, actually, we somehow know already that for 4-point case we have only 1 independent amplitude, so there must be something more going on, because now we still have basically 3 independent parameters, namely the ns, nu, and nt. So there must be more dependence between the numerators. And indeed, now just take all these amplitudes and insert it in the BCJ relations. So when you insert this in the BCJ relations, you get a relation between numerators. So insert amplitudes, and these 3 partial amplitudes into BCJ, and what we will find is NTs, NS minus NU. Now this is from BCJ relation. So there's now that means at least we have only 2 left, which is still not yet the final answer, because we now knew already kind of from the KK relations that there are only 2. Okay, so let's just maybe move on now with let us define structure constants. So I just define structure constants. I mean, actually the structure constant, how they appear when you compute this Feynman diagram. So now that when I compute here, I have a structure constant A1, A2, A, which is then contracted with the structure constant from here. Alright, so this everybody knows, right? Everybody knows what the structure constant is. Yeah, okay, so it's structure constants are I mean this 3 symbols which you get from the commutator, from the anti-commutator of from the commutator or from the anti-commutator. You see, I don't know. But because I usually, so the crucial relation is that you can convert them into traces over these group factors, and these are usually the guys I could usually compute with these guys, and then for example there's another relation. I mean this actually then turns into 1/4. 1/4. You put this together, and you have a sum over. When you compute this Feynman diagram, you have a sum over all color indices you exchange. So in that case, you sum over all zeta, and this gives you, in that case, so in other words, each of these propagator diagrams will come with such a tracer, which equally you can just write as combination of structure constant. And now similar, so of course this is I write S because here I have 1 and 2 coming together, and then with 3 and 4, so this is very much resembling the S channel, and then I have FA2, A3, C, FC, A4, A1, and then I define, so this definition, CT, and F, sorry, completely analogous way. I cannot guarantee here for the, there might be some, depending on the group, some additional factors, but this will not affect us now. So there might go, let's be on the safe side, let's write an alpha here. And alpha depends on beta, but it also depends on which group you are considering, but it will be not relevant for us. So that actually the only thing what we now need to know now is, there's a Jacobian relation between the structure constants, and this Jacobian relation can be written in kind of these 3 parameters like that. So now you can compare what we have found here via the BCJ relations and what is in the effect from group theory. and this relation look very similar, and that is what Bernd Carrasco-Johansson called a color kinematic duality. So simply the fact that you have two relations which looks the same for the numerators, which is kinematics, and color with the structure constant relations.
This extends to higher points.
Yeah, that is now the next step. How this will be extended to 5 points and so on. Okay, so this is color kinematics duality by Bernd Carrasco-Johansson. And now, just for completeness, you can write down the full super Young-Mills amplitude in a nice form. Now this is so of course you start with the formula I gave you some lectures before. So this is Young-Mills coupling squared, and then you sum over all permutations Sn minus 1, and you have trace TA1, TA pi 2 times TA pi 3 and pi 4, and then the corresponding sub-amplitudes. And you can indeed check, which I did with some Python, that this, I mean, now here you insert all your amplitudes with this ansatz, with this numerator ansatz, which was written here, and then you take for each of the diagrams. I mean, you have this traces which in tune, which you can also treat as this structure constant, or you can write this CS or CPU and so on. And to this end, this can be computed to be so you see also here that color in kinematics is kind of completely the same level here. So this is a final answer. So this is of course much simpler. So this is a full 4-point Young-Mills amplitude. So now, how we complete this 4-point case? I mean, as I said, I mean, we now already have relations between, let's say, we can express, for example, all n keys and nc keys by this tool, but we can do even better or even more. There's a lot of freedom to choose numerators, which we have already seen by this ansatz. By just, for example, we could have put the 4 vertex either to one numerator ns or to another numerator nu. So indeed, we can there's a kind of gauge freedom. So, I mean, which is like gauge freedom for the numerators. There's a lot of freedom to choose numerators.
Sorry. The CS, CU, and CT were appearing inside the color strip, right?
The C's up here. So
they are in A, not in this space.
This diagram
with fixed color, yeah. So they are in A, not they
are not in A.
They're not in A. They're that trace.
No, this is really the Young-Mills amplitude I have written here, which was so. For example, this is so again. This guy is this diagram plus the corresponding U channel.
Yeah. Okay.
And
inside there are the structure constants.
Okay, I see that this is now not the same notation, because here I should get the as a CS structure from here the CU.
So okay.
So okay, so it's yeah. Then I just I better erase this.
So that one goes inside, or do you have absorbed in an S and U afterwards? Yeah, I'm a bit confused on where all the
I see the confusion. I think the confusion is can be removed if you just remove this.
Yeah, this way, of course. Right? then everything is there for sure.
Is there. But then I simply define this guys to be CS. Okay, then.
But you defined in the first lecture that all the color part is out. So the alien mix is anything else but the color.
Yeah, but these traces there are not exactly the straight ones. I mean, you have generators on the external layers, and then these C's have a fixed A1, A2, and are summed over C. So it seems these are the structure constants that come from the vertices. So in the Young-Mills strict amplitude, which was what I was asking. So I don't know, naively I would say that the trace there was okay. And these C's were inside because they come just from the vertices, but maybe I'm wrong. Quel fattore lì.
I mean, this is a young. I think it was correct. Yeah.
Yeah.
I think it was correct.
Okay.
Without putting the C's, yes. Yes, because. Yeah, I think it was correct.
So then you are absorbing in NS and then U and T this factor of the trace in the second equality.
Then I'm absorbing NS is inside here clearly?
I mean, yeah, that trace goes somewhere in NS and U and T in the second. I'm just asking because this NS and U and T were fixed by the relationships before, yes. And they were fixed using the color strips.
Let's make it precise. So this I said gives an S and U, and okay, this was also how we defined them from the beginning without the color factor. And if I do this, then I write T1, T2, T3, T4 times this guy, and I think I don't completely remember, but I think it is precisely what I some day ago did. That if you now do for the remaining diagrams, then you can rewrite the traces and combine it into this by this relation. You can combine it into this color factors.
Okay.
I mean, yes, I begin to remember that. This is of course very likely because remember we had this other diagram which had minus ns. I mean, you can also just try to.
Yeah, but it was seeming that the CS, CU, and CT were appearing at the level of the single diagram. They are part of the vertices.
So here these come from the combination of all the diagrams.
I mean, there is a vertex in QCD which has a structure constant there, and it's
so here.
It seems there's that
one. So remember the second diagram was NS and T over T, and this was a color ordering T1, T3, T4, T2. So this gives me a second piece from here, and when I combine all NS terms, this they will combine the commutator terms, which then I can rewrite like that.
That I see. I don't see exactly. I mean the relation. I mean that was much clearer in terms of the single diagram vertex, which has an FABC and there's another FC A1, A2, and then you exactly get that. But now somehow this seems to come from a combination of diagram sets. So
yeah, but this is the case.
Okay.
This is the case, and I mean it is clear that that I did another computation a long time ago. I remember that I checked that all propagator terms can be written in terms of this productive commutative and color commutative.
Okay.
So I think it's completely correct. It's, of course it takes some work to combine all NS numerators, for example, to here and to recover this product of commutators.
Okay, thank you.
So this is nice homework to check. And if in the unlikely case, you really see some puzzle, you can write me an email and then you can sort it out. But this should be, it should be like that. Okay. So now, as I said, there's a lot of freedom to some kind of gauge freedom to change the numerator. So what you can do is you can just just look what we need here for our ansatz. I mean, we might just shuffle stuff from this numerator to this numerator and vice versa. So we can introduce new numerators by let's call it the gauge transformation, which is of course not a gauge transformation. So this is alpha is just a generic function depending on all kinematics, which like we conduct for in the action. Then we do this. Clearly, this the only condition we have to fulfill to do this transformation is that we have to preserve this relation, because this is also a relation which, so to say, which follows from the Kleist-Kolfe relation. So that, of course, we are not allowed to change them. So this relation clearly fulfills this numerator relation. So this, of course, when you look here, it has the effect that we reshuffle effects reshuffle effects from the 4-point from the conduct terms. We get that these two numerators. So this transformation is the effect of moving between S, T, and U. General diagrams. Now we can take some gauge choice. Maybe we can even choose one numerator to be 0. So we can take alpha as a u over u, and that of course means that u prime is 0, and of course then the relation is here, and then you see clearly there's only one independent numerator. I mean, I can solve for one of them. So from here you see there's only one, or in the other case. So the BCJ relation told us it's in total n-3 factorial, so in 4-point case one independent numerator. So this is everything what can be said about the 4-point case, and now we see how things change when we move to higher point cases. So what we have learned from the 4-point case is that we do not really need to write down all these ansatzes for this Young-Mills amplitudes with all numerators. So in the 4-point case we wrote down 3, but then we immediately found out that by plugging them into the Kleist-Kolfe relation they are fulfilled. So Kleist-Kolfe tell us that we need only to consider n minus 2 factorial amplitude. So this is what we are doing now. Was from the beginning. So we only write down n minus 2 factorial amplitudes and define by writing them down the numerators. Just in the like in the 4-point case, we wrote down these amplitudes and by that the numerators were defined. And recall that we had to make sure that in new color orderings the same numerators are used wherever they have to be used. Like there were diagrams where the numerators just appear with a sign flip from other diagrams. So to this end, let me just make after applying finish the sentence, the clear relations. You have 6 for the 5-point case, 6 partial amplitudes. And this we have to write down in order to define our numerators. So it is convenient to define these 6 in the following way. So sigma now minus 2, which is of course and recall. So let's do it. Recall to what we did yesterday with slicing our pentagon. This Euler polygon division problem gave us a number C3 is 5. So that means we did this for this canonical color order. We have five different compatible channels which can appear for this color order. So we write all of them in the numerator. So this poles we have already seen in the corresponding diagrams to be associated to them we have seen yesterday already in quite much detail. So this is now, so far it's completely analogous to the 4-point case. Of course, for higher points we need to expect more numerators, not just 3, then more. And so in the first diagram in the 4-point case had 2 numerators according to this Catalan number, and now we have 5. And now we have to write them in a similar way for all 6 of them, so then it's in total 6. And clearly now, sum of them will again imply these numerators we have already defined here with, for example, minus signs and things like that. And to this end, if you do this exercise, you will find that there are 15 numerators. So to be compared with 3 numerators in the 4-point case to start with. So there are 15 numerators. In fact, this you can do for any diagram, for any endpoint amplitude up to this stage, and you will find a certain number of numerators for any external number, and so this number is can be computed. So this number is given by this formula. And recall for the endpoint we write down n minus 2 factorial of this amplitude. So that you can compute 2 times 5 is 10, minus 5 is 5, so this is 1 times 3 times 5. So we have 15 numerators for n is 5, and you can compute for 4 it's 8 minus 5 is 3, so it's 1 times 3, which is this 3 number. So far so good. And
So the way to fix them is just to write down everything, and then we use KK relation and fix which are equal.
Yeah, we don't use KK relations anymore because we just focus on those 6 independent one, which this.
Okay, so then that number just follows from the number of compatible. But
yeah, we have to make sure that of course there will be diagrams which, for example, there will be color orderings here, which again implies these 2 poles.
Okay,
and then we have to make sure that we don't introduce a new numerator, which actually is maybe minus n3.
All right.
So you have to think a little bit, and in fact think about all diagrams and write them out. We did it.
So it's okay. So this step is not automatic. We need to think about the
diagrams.
Yeah,
we need to think about. I mean, we did with Dimitris Simpis and Carlos Mafra and Oliver Lotter. We did this in a paper for 6 point, and really have to sit down and think about how to get for 6 point. You have then 24 of these lines to think about. But of course you can automatize it. So this is now we can, in a similar fashion, recall that this each of this numerator again corresponds to a certain diagram. So here we have the first one is of course we have a propagator S12, S45, and now let's just define in a similar fashion. Introduce let's say the corresponding structure constants, which would correspond or which you would get by computing this and putting the vertices together. So we can define again this definition. We can define this product of structure constants. Now, of course, you get from the 3 vertices, so you get a product of 3 structure constants with sum over the internal color. C1 and C2. So this is sum over C1 and C2. Now this is completely obvious generalization from what you did for 4 prime, and then you have, of course, this guy. And so forth. It turns out that there are again 15 of these guys, and again you can now write down you can write down the full color decomposed amplitude in the same way as before. So we start with writing sum over all n-1 factorial sub-amplitudes times group traces, and then we can further reduce it to this 15 terms. So recall in 4 point case we have just 4 terms. And here I just collectively denote we have some propagators as ID, which refer to this numerator.
So the first line is C1, the second structure constant, should it contain an A2 or a C2? There. Not that, like the second one.
Yeah, it should be a C2, I guess. Yeah, it's a C2 thing to say. So of course now we have again, or actually what is used here already is Jacobi relations. So we can just write them diagrammatically. This is Jacobi relations, and we can. So let's recall. So Okay, to make it recall, we had this Jacobi relation to four case, which I write diagrammatically. So this was implies the color factor CT. This is CU and this CS, and recall that okay. And now what we want to do now is see how this what this Jacobi relation corresponds to in the 5-point case. So actually what we want to now write down the Jacobi relation, so we just replace it all 2's with a 5 and all 4's with a 2 and all 3's with a 1, and then we should this Jacobi relation, I mean, in this structure constant, we also do this replacement, so we will get something like FC A1, A2 from here, and FC A5 B, or I write B or 1, so I should replace the 1 actually with a B. So this structure constant clearly corresponds to the blue labels by converting this exchange diagram, and then I have for here I have BA2, so BA2, and then sum with C A1 I5. And for this, I would take F BA1 C F F C. BA1C, and then CA2 A5. Okay, so this is now just associating to this new labels this corresponding structure constant, and now I mean this is minus, and this is an identity. This is just a Jacobi relation, and I can now multiply the whole relation with FA3 FA4B. I mean the whole equation and sum over B, and by that I get a relation. By that of course I clearly get something which comes out from the 5. And I get a 5 relation between this 5-point color factors, which is which is just multiplying this. So which I now just write in terms of diagrams. So then this means I extend this diagram with an additional exchange diagram. And what this does is of course this will be preserved. So what this will give me is the following diagram now. So the 1, 2 stays here. Of course I have this propagator, and I have the 5, and this B part will become an exchange diagram, and then I multiply here with 4 and 3. So this is the diagram I get as manipulation, and then this is in terms of color factors. so what the 4-point diagram was, that was just something here. So is this clear what I have done here? I mean, this is just trying here to explain in a pedagogic way that is how we obtain this structure, this Jacobi relation for the 5-point color factors. And indeed, this guy, I mean, you can convince yourself is actually C3. So what do I mean with C3? This would have been here the next guy to be written down. Huh? So it would be the guy which corresponds to this diagram, the color factor. And indeed, this has pole 3, 4, and 1, 2. So this has pole in 3, 4, 1, 2. So indeed, the color factor corresponding to this diagram is C3. So it is, would have been this guy to be written here. And now you can, I mean, just do the bookkeeping. I mean, this is C5 and this is C8. So indeed, C5 we still see from here it would be this would correspond to this numerator. It's 5, 1, 3, 4. So indeed, this has 5, 1 and 3, 4. 3, 4 propagator. So these are two diagrams. Of course, this was precisely the reason why I chose it in this way. These are two diagrams which appear already in this expansion. While the 8 is a diagram which appears in the second or third amplitude ansatz. So, what we have seen now to be a factor is that, I mean, we have kind of rewrite this Jacobi relation for this particular diagram. So let me write down it again. And then according to the color kinematic duality we have seen in the 4-point case, we would now expect N3 is equal to N5 minus N8. So N3 we have seen is this guy here, which is of course denotes all the kinematics appearing here, and N5 is here, and then the N8 would come from the next ones. And of course expect and further such relations. I mean, now we have many more because we have more numerators. Over all 15 NIs. However, now comes the payoff. This only holds this relation, so this color kinematic duality can only be imposed for special choices of these numerators. Recall we have a lot of freedom to choose these numerators by putting the 4-point vertices either to one numerator or to another. But here, I mean, you see now in the 5-point case we had 5 numerators. There's a much more freedom to choose the numerators in one of these. To choose the numerators by grading the 4-point vertices. So this only holds for special assignments of the conduct terms. I mean, grading the conduct terms is the numerator. So, in other words, in contrast to the 4-point case, this relation does not generally hold for any. So we have seen in the 4-point case, we can choose any numerators. I mean, subject to this transformation n goes to n prime, and we always could make sure that this is color kinematic duality holds. But this is not true for the 5-point case and for the higher point case. So we contrast them. So in contrast to the 4-point relation, the 5-point relations, which would be of this sort, generically do not hold. I mean, this I have already said, so the quadratic interaction of the gluons exhibits an ambiguity in the decomposition. And so in the decomposition for how to arrange these numerators of gauge amplitudes with respect to diagrams with cubic lattices. And the color kinematic duality depends, as we see, heavily on to get the right numerators. And so why is this nevertheless? Why is this so important? I mean, actually, so this color kinematic duality is according to Bernd Carrasco-Johansen, and they're heavily using this. I mean, they're not doing trivial computations; they're doing actually five-loop computations. So the nice thing is actually you can now draw loops here, and these relations also hold, or they are assumed to hold. So, so for example, you can now, as we did here, you can embed a given color kinematic relation, a given numerator or given Jacobi relation into a higher diagram. So what we did here, we just upgraded this to a 5-point diagram, but we could have also upgraded it to a 1-loop diagram by attaching this loop here. And then these relations also turn out to hold these numerator relations, or they clearly hold for the color factors. And then what Bernd Carrasco-Johansen and Reuber are mainly doing, they're searching for numerators which fulfill this color kinematic duality. Because having such a relation that would drastically simplify the higher loop computations. So, and in fact, the reason why, I mean, they're doing this five-loop for graviton amplitude computation to check UV finiteness, and the main reason why they haven't yet completed this because they haven't yet found the right numerators to apply those relations. And those relations you would drastically, as we just see here, would drastically simplify the result. You can boil down everything to.
Is there any guarantee that this thing continues, that there is at least one reshuffling of numerators that gives you the color kinematic duality for any number of points?
Yes, this is precisely string theory. Okay. This is what would have been
also for higher loops.
That is not clear. I mean, we have checked at 3 levels that string theory gives you by 3 automatically these numerators which fulfill color kinematic duality.
Because if I understand, I mean, all the things we did in string theory were heavily relying on the fact that the worship didn't have holes, right? So,
can you say it again?
But I mean, up to now, what we have seen for string theory was heavily relying on the fact that the worship didn't have holes. So it's not. I mean, I don't know if the methods are the same. It's
so by that you want to say that it's not guaranteed whether we get also this takes over to higher loop.
But it's not, at least I don't see it guaranteed.
No, I completely agree. That I mean, I'm not. I mean, we had with Carlos Mafra and Oliver Schlotter, we 2011 we had a paper to derive this numerator at 3 level from the string amplitudes, but I'm not working in 1 loop because I'm also a bit skeptical whether you get this numerators from the string diagram at 1 loop, but Mafra and Schlotter, they seem to have some results at 1 loop. But I don't know how this continues. It is believed or it is hoped that the pure spinor technology will also provide you by phrases numerators just in the same way as at 3 levels. So Okay, this brings me to my final comment before the break. The lower energy limit of the superstring amplitude naturally selects its numerators. You get a unique choice of kinematic numerators, which will satisfy numerators ni. Which of course is the main point, which satisfy all Jacobi relation. I let's write all dual Jacobi relations. So for each numerator relation, I have a dual Jacobi relation. And so for this is, I don't want to go into detail because this would be now beyond the scope of this morning lecture. For that, of course, we have seen that we start now with a n-2 factorial ansatz. So for that, we actually we get it in the intermediate step. Recall it at the end, we write down the superstring amplitude in terms of n-3 factorial building blocks. But we stop the computation before we arrive at this n-3 factorial by having n-2 factorial building blocks, and from them we can precisely read off these numerators and which fulfill all these kind of kinematic dualities. This is, you can see in the paper. Now this is in the archive paper 1104. This macro and are there further questions to this? Hello? Everything is clear? You want a break? No. Okay, then let's make a break.
Christoph Kappa.
What section? I think we are 7 electron section. So this is now, of course, in context to the previous lectures, but it's also kind of independent because it is about the mathematical aspects of this amplitudes. Indeed, there's a lot of mathematical structure behind it, and I was in the last 3 weeks I was in Madrid at the mathematics department for a workshop on multi-zeta values. The problem, let me phrase what we are doing. Actually, we have very much, when we looked at this Worldsheet integrals called C, and just an example, we have very much considered the field theory expression, or the field theory part, which is just the lowest order in the alpha prime expansion. So this is just one of these typical objects we have. Now I write just the alpha prime outside of this exponent to clearly see that we want to have a power series and consider power series in this Mandelstam's So we might have C1, C2, C2, C3, C3, 5, C5, 4, and C4, 1. And of course, this then still has this conformal killing group factor to cancel the infinite when you put 5 at infinite. So this would correspond to the integral as C1, C2, 3, 5, 4. Okay, this is some of these colleagues we have met already. And we have also, I forgot, today at the beginning I forgot to write down use a general theory. Having such C, I mean, yesterday we played a little bit on how to extract the singularities, and then we saw that, okay, from here, looking at here, of course, this clearly has a pole in 1 over S2, 2, 3, and in of course, only 4, 5, and 1, 2, and then we somehow, by some, I mean, spend a lot of time drawing these diagrams to see that eventually that we have only this allowed or compatible poles appearing. So this might have been an example we have discussed yesterday, but then I promised you that actually there's a general theory of how just by looking at these combinations, how to get this, how this is expanded. So I simply forgot in the module to tell you the theory, so I can either at the end of my lecture or you just look in the work of Tusa Oblast here with Johannes Blöden and Oliver Schlotter and myself. Some 1304 paper. But now, of course, what is the next? Of course, more orders. So this is an expansion in alpha prime. So this is, of course, alpha prime to the -2. And I should also write it down now. Or maybe let's do it like that. Because I mean this is the lowest order, and then the next order is actually from alpha prime to the 0. So we need to compute this, and when you compute this, you get something like that. And in the last lecture, we would like now to understand the structure of these higher orders, and in fact, we will be able to see that these higher orders can be grouped or put into very nice structures that we essentially don't need to compute them anymore. So that everything is given by the structure of the amplitude. So this is a typical example which has to be from which you can, for example, then in the 5-point cases are terms which probe the alpha prime, which probe, for example, the f to the 4 terms in the one infinite action. And in order to understand the structure behind this, let me first define what multi-zeta values are. So you clearly should expect when you expand it higher, you should. I mean, you see already that this zeta functions appearing, and in the generic case are so-called multi-zeta values, which are defined as follows. So let me. I have a special definition, which I want to write down now. So multi-zeta values are simply generalization of the single Riemann zeta function. They have several objects, several integers, entries, and actually the numbers of integer, which is r in that case, is called the depth of the multi-zeta value. And this is then just the generalization of the multi-zeta function, which has the depth 1.
The multi-zeta values are defined just for integer entries, but also for complex.
I only need them for.
You need for integers.
I only need them for positive integers, but of course you can analytically continue them to higher integers. So you need, to be precise, you need n kr bigger than 2 and the remaining and 1 up to n r minus 1 and then 1. In order that it converges, but you can.
Maybe.
Huh? So here so this is the depth of the multi-zeta function r. So you have depth r, you have r, so it's integers, and the weight you also associate the weight to it. The weight of the zeta function is just the sum of these integers from I to r. And now you have all seen already zeta 2, zeta 3, and so on. So in fact, these zeta functions span a commutative graded Q algebra. So you have an algebra which is graded. So it's a direct product of graded subalgebras from 2 to infinite. So that means for each weight you have an algebra. So you can take multi-zeta functions of a given weight k and combine them, and you just get relations between them. So you combine them in Q. And a simple example is that you can, for example, at weight 8, you can, for example, have zeta 2 to the 4, and you have zeta 3 times zeta 5. So you have an algebra, and you can multiply them with some coefficients, and you get some other multi-zeta function of the same weight. And now there's a conjecture by Sartre that you have actually a basis for each weight, which this basis has a dimension, and each multi-zeta function of this weight can be expressed in terms of such a basis. And this dimension is given. So this is defined to be the dimension of each of this subalgebra, and this subalgebra, this dimension formula is given by dk's minus 3, and you start with just define. So by that you can choose a basis at each weight, and then a given basis is so we have here the weight. What do we do? 3, 2, 4, 5, 6, 7, 8. So you can compute this number. Of course, for 2 you have just a one-dimensional basis. There's only zeta 2, and for 3 there's only zeta 3, and for 4 there's only zeta 2 squared. For 5 now it becomes more interesting. There's zeta 5 and there's zeta 2 times zeta 3. That means, for example, any zeta function of weight 5, like for example zeta zeta 2 comma 3 or zeta 3 comma 2, so the value of 25 can be expressed in terms of these two basis elements. So this is precisely the statement. So you get a linear combination of them. And of course, if you want, you could also just say, okay, I don't like this basis, I just take this basis, which you actually call Hoffman basis. I mean, this Hoffman basis has just 2 and 3s as entries, but you introduce multi-zeta values. So this basis, what I'm writing down here, is a particular basis, and actually this is basis uses that you stay at lower depths as long as possible. So that means here you see we are still at depth 1, and so this is a basis at weight 6. So you have zeta 3 squared, clearly in zeta 2 to the 3, and at weight 7 we have zeta 3, zeta 5, zeta 2 squared, zeta 3, and zeta 7, of course. I think that's all. So maybe then you can just compute the number. So D7 is D5 plus D4. Okay, it's 3, so this is a complete number. And for 8, and now the dimension is 8, so it's 4. So D8 is D6 plus D5. So this is 4, yes. And this basis. So the main point is why I wrote until 8 is because there's the first time you cannot write basis only with single zeta functions. You need a zeta 3, 5. You have zeta 2 to the 4, of course, and you have zeta 3, zeta 5, and you have zeta 2 squared times zeta 3 squared. So
this requires that the ends are all positive, or you can.
Yeah, I'm only talking about positive.
So the year's conjecture implies only positive.
Yes. Yes. We are not, and there's a general theorem that shows these are so-called iterated integrals. Iterated integral means if you have an iteration here, it's an integration relation. These iterated integrals always lead to multi-zeta function. So there's not any other mathematical object which might appear here. I mean, let's say Catalan number or any other transcendental number. So there are always multi-zeta functions. So we will always stay in this algebra. And so far it's just some mathematical facts. But in a moment we will see how this can be, how this nicely fits into this alpha prime expansion. So now, of course, you can say, let's say I'm at weight 10, and I have a given multi-zeta function, and so at weight 10 the basis is 7-dimensional, and then I write down here the basis which we can choose at weight 10. Then maybe coefficients will come here, and this is precisely the crucial point now, how to determine these coefficients. So we want to expand a given multi-zeta function of weight 10 in terms of a basis of this table. So how the question is now, how can we determine this coefficients? Of course, you cannot just turn on Mathematica and ask Mathematica to compute these coefficients.
So can you orthogonalize this basis? Can you orthogonalize this basis with respect to some internal product?
You mean orthogonalize?
I don't know, take an integral and get rid of all the rest at one coefficient at a time.
Get rid of?
All the I mean, get an orthogonal basis out of this basis and use it.
Yeah, this is actually will be precisely happen now.
Okay.
This is actually will be precisely happen. We will map the whole problem to a different algebra where the coefficients become nicer, sort of. So this is a basis. So you see, there's also at weight 10 depth 2 guy appearing. And now, so how can we compute these coefficients? I mean, I tell you what the coefficients we want to compute, and indeed I will give you an algorithm which computes these coefficients for you. Of course, this according to this, because we are talking about Q algebra, these are coefficients in Q. And here's a coefficient 1. And this has been done by, so this algorithm has been done by the mathematician from Paris to Oxford, Francis Brown. And so how the question is how to determine this coefficient. In Q. And for that we cannot solve the problem with these multi-zeta functions because of several reasons. First of all, we don't know whether the Saki conjecture is true or not. I mean, it's just a conjecture that has dimensions. Also, we do not know how for example, weight 50, how the basis can be constructed. And furthermore, there are some relations between multi-zeta functions called Shuffle and Stieberger relations, which are also not clear whether they hold at arbitrary weight. And third, we want to do some computations with this guy. That actually we want a Hopf algebra structure for these multi-zeta functions. So what we do now is we consider their motifs, and for them we assume that the Zahido conjecture is true, so we can successively construct the basis at each weight according to this conjecture, and we assume that all Shuffle and Stieberger relations are true, and we assume that all Motivic multi-zeta values span a Hopf algebra, so we can use some Hopf algebra in particular as a coproduct, and this we can use. So we can solve this problem if we go to their motifs. And let me first can give you the definition, the clear definition of what motivic multi-zeta values are. And then, so motivic and now they are denoted with an M here. So this means that we consider motifs, and so in other words, we will be able to compute this relation with the coefficients. We will only be able to compute it by their motifs. So this is what we will be able to compute in a moment, and then we have to assume that the motifs just describe also the real zeta functions. It gives us the definition. So the motivic multi-zeta values are defined as elements of a certain Hopf algebra by H, and of course it's also a graded Hopf algebra, just like here. Graded with the weight. So in particular we assume everything what we know about the ordinary zeta function about them. So for example, a weight graded over Q, which is graded range. Which is graded for the weight. W. And now this gives us the possibility to go back to the, let's say, classical multi-zeta functions, and we keep with a period homomorphism. Or period homomorphism. Which is called pair, and this is a map from this algebra. To R. This is a surjective map. So there are many more. Presumably, there are many more Motivic multi-zeta values as real zeta functions, and the map does pair of a Motivic multi-zeta value. Of course, you can guess what it should do. It just projects onto the real zeta function. You might be worrying, because actually when I read this for the first time, why is it called period map? I mean, period map might sound a little bit too much for this trivial operation, but zeta functions are periods. So periods are special numbers, which is a set between which in particular you can sum of the transcendental numbers like multi-zeta values. Periods are quite generically objects which you can get from iterated integrals. So I have given you one example a few days ago how that zeta 2, as far as I remember, is given by some iteration of dx dy 1 minus xy, and as far as I remember, this is like something like zeta, and this is a period. So you have an iteration here. So the integration region is given by a you can describe it by polynomial, and I mean, this is a triangle which you can describe by polynomial, and you have a rational function here. This is defined to be a period. So you map this Motivic multi-zeta values to such object, to such periods. So now we just continue working with this. This is in this Hopf algebra. And so what we have now is we can map from the Hopf algebra to this zeta function by the period map. But actually, so here we have the Motivic guys, the ordinary guys. But actually, in order to really do or to establish such relations, we now map to another space, script U. So that means we need a mapper which is called the phi map, which maps each multi-zeta function, each Motivic multi-zeta function to some actual non-commutative space, which is spanned by an alphabet F3, F5. So this is a Q span of these odd generators, tensor with S2. So this is the algebra module, and so what is this map? Of course, to formalize here with this, actually this map is defined to be in the following way. So each single zeta function, and the Motivic one, are mapped to these generators. So you have a fuse one here. And these are non-commutative. So these are non-commutative. So you can build words out of these letters. So like for example F3, F5, which is not F5, F3.
I ask a couple of questions. One, you said that the map, the pair map is not, the period map is not one-to-one. So this means that the XIM and Motivic zeta function can be mapped more zeta function, normal zeta function.
It's presumably a bigger space. It's presumably a bigger space.
So, but the base elements, because then you want to derive relation so that you can determine the coefficient for the zeta m, and then you claim that the decomposition also is valid for the multivariate zeta bar.
Via the period map, yes.
Yeah, but what I want to say, does it map? I mean, there is a correspondence for the basis elements one-to-one, or not?
Well, you can construct your basis element one-to-one up to a certain weight, and you can so to say experimentally prove that the Xavier conjecture is true. But you don't know what you can do at weight 50. You can also, according to this table, you can of course assume that the Xavier conjecture is true and write down a basis, but you don't know whether it's true.
So if you believe the conjecture, you don't even need to go to a motive.
Well, it needs to determine the coefficients.
Can you ask?
I mean, as far as I understand now, you're creating this new space in which is basically defined by saying all the conjectures are true.
Yes.
So if you believe the conjectures, you can just remove the n, right? So that's the point.
Yeah, I mean, experimentally, I mean, if I say that I just believe the conjecture is true, I could just remove the m.
All right. Okay.
And I have the relation for them, but I need to go to this Motivic. I mean, in a strict mathematical term, I need to go to this Motivic because I want for them I explicitly assume that the conjecture is.
They're defined by saying that those conjectures are true in this other space.
Yes, and moreover, I want that this is a Hopf algebra. For example, this has a Hopf algebra has a coproduct, so I can which is called delta. So this coproduct maps a zeta function to. So it's the opposite of a multiplication. So it makes two elements. So here we have a certain weight n. And then you get products of smaller weights, and then there are lots of combinations. And this is very, very important. And this coproduct, so you get this is coproduct. This coproduct is actually very important to construct this map phi to this space here. This is not this I cannot do now in the lecture because this would take me another 15 minutes, which I need for something else. So this coproduct is how to construct this map phi. So this map phi is defined to be like that for the basis elements, but this is not all. I mean, you need in order to I mean, this is definition. You do not know what the map does on, for example, zeta 3,5.
Okay, so that was my second question. So because you are taking phi on Motivic zeta values, which are odd,
yes,
which are depth 1 and odd weight. That's defined only for those, or
exactly. It's only defined for those, and for the others like even weight or higher depths, this map is constructed recursively by some recipe. Let's put it like that. And the recipe goes via the coproduct. So this is the first condition for the map, and the second condition for the map is that you assume that you have a given zeta Motivic zeta function of weight n plus 1. and then you say that the map is a basis expansion in terms of this letters up to the weight under consideration. So you expand this in terms of this little alphabet, I mean letters, and with some coefficients. So this is actually not zeta, it's xi.
So this is a phi of z, and then there is a sum over some coefficient xi
times this alphabet. Okay. Yes. So just an example, and of course the heart is now also.
What about zeta 2? What about zeta 2?
Yeah, zeta 2 is special as zeta 2 is mapped to F2.
Okay.
And the F2 is just tensored here.
Okay.
And F2 commutes with everything. So I can write F2 anywhere I want it. And so what is now the heart is of course how to compute this coefficients xi. And these are guys, the whole thing according to this mapper, this should be mapped by phi. So phi of zeta m should be now weight should be also weight n plus 1. I forgot to say that this is also a graded with respect to the weight. You see here it's graded, so here I have weight 2k plus 1, and here I have also weight 2k plus 1. So that means since this is 2 plus r, this has to be an element of n plus n minus 2r to be in total as written in the of this rate. And so you see somehow that this size of smaller weight and how this map is constructed is actually you take a part of the coproduct and actually you take this part of the coproduct where this piece here is of this weight, and for this piece here you apply you take a certain coefficient you take a phi map which is already established because this is of lower weight. So I don't. At this point, I just wanted to sketch how this map can be constructed via the coproduct, but I don't want to go into detail. Or is there some important question on this now? So what you can now, for example, construct the phi map for this guy, just for at this point just for fun. And as I said, there is a rule how to compute this phi map. Okay, there are now I think just some trivial example. As I said, phi of any of these guys is according to the definition just maps to the letters. And then phi of zeta 3, zeta 5. Now this is here we are in the software algebra which is commutative. So it cannot just be. Of course, we know that each single zeta function is mapped to F3 and F5 accordingly, but it cannot be just this because here it's a commutative object and here it's non-commutative, so it has to be symmetricized and this is done by the shuffle product, which is just shuffle product of these two guys is f3 times f5 plus f5 and f3. And similar then, for example, for this guy, zeta 5 squared, we get the shuffle product of f5, f5, which is 2 times f5 squared. And this will really have to convert, and is minus 5 f5 f3. So now you see already what is going on here. You see that we gave up this higher depth concept at the cost of introducing non-commutativity. You see that this is clearly different from here. So this because this is f3 f5 plus f5 f3. So I cannot. It's non-commutative, so I cannot put it together, and so it's clearly different from this. So you see that we really distinguish these two basis elements. They are distinguished by the non-commutativity.
How much time do you need?
1 day.
Will you resume tomorrow?
Yeah.
I'm serious. Because,
it's about resuming tomorrow.
Minutes. No, maybe you can. For those who are interested, you can arrange a bunch.
So
we can do
after lunch.
after lunch.
So how many minutes I still have?
0, minus 15. Minus 10. So.
You want to
Yeah, but some people are
fare la
afraid.
fine di Lorenzo Bianco?
I know, but
Ma lei ha-
Facciamo
Okay,
sto
actually,
pomeriggio.
sto pomeriggio
Continuiamo.
I would just need maybe 5 minutes, and
Okay.
then I can. When does Fernando's lecture start?
In 15 minutes.
Half past. And maybe they want to have the rest of the students. So.
Well, there's all Fernando's lecture for
Eh?
resting. All Fernando's lecture for resting, right?
Okay, we have now this map, and let me try to. Tell you the highlights in the next 5 minutes. Let's go back to the string amplitude. So recall the string amplitude was a vector in -3 factorial vector of string amplitudes. Color with different color ordering, and we have written it in terms of this matrix C times S times the Young-Mills vector, right? And now actually that is how we originally found the result by computation. We introduce a matrix F here combining these two guys. And so recall the C's are all these iterated integrals which have this alpha prime expansion. And have this alpha prime expansion. So now what we do now, we consider the Motivic superstring amplitude. So we put an M everywhere. Of course, Motivic Young-Mills is the same as Young-Mills. So this means essentially means that we replace in this iterated integrals after alpha prime expanding them all multi-zeta functions by their motifs. And now, so this is an expansion. So now we consider phi of this Motivic. So recall this is an n-3 factorial times n-3 factorial matrix. And now we compute this. So this will of course be stay a matrix. And now we compute it, and recall this is highly. This is a infinite power series in alpha prime, so it has all this multi zeta values and so on. And as a result is. So of course this phi is a more, as we have seen, is a morphism, so it will act on essentially on the Motivic multi-zeta values, maps them to this non-commutative algebra module, and we will get this. I will explain in a moment what this is, what the M and the P are. So you see, first of all, this F takes an extremely simple form in this Hopf algebra, in this U Hopf algebra, and extremely simple, and the only let's say physical objects entering here are these matrices M and P. And they are defined in the following way. So m2k plus 1. Of course, the whole thing is n minus 3 factorial times n minus 3 factorial quadratic matrices. So this must be also n minus 3 factorial times n minus 3 factorial matrices. And this is just the zeta 2k plus 1 part of this. So this is of course a matrix containing all the Muddelstamms. And P2k is the corresponding zeta 2k part. So you see now that also, I mean, indeed, there's at weight 8, there's higher depths, multi-zetas appearing, zeta 3,5 and so on, but you don't see them here anymore, and the whole superstring amplitude is specified just by the single zeta part. And moreover, I mean, I should stress again, when I wrote this table was highly dependent on what basis we choose. We could choose this Hoffman basis with, for example, here zeta at weight 5, zeta 2,3, zeta 3,2. But now you see this is completely independent of what basis we have chosen. And this is precisely, in the lines of what also people did with in Young Mills with a symbol. So it's a completely basis independent relation. We don't need anymore to talk about this Schaffner and Staffler relations. And Schaffner relation is something like zeta m plus zeta n is zeta m plus zeta n plus and something else. I mean, of course, you can easily prove it because you can do by partial fractioning. So we don't need all these relations anymore because they are just built in here. So you can write it in a simpler way. And so this is a full Motivic superstring amplitude. I think it does not recall this contains all orders in alpha prime. And so the recall these matrices, which are the only building blocks, are n minus 3 factorial. So I just to formalize it for 5-point case, and then you have 2 by 2 matrices. The P2 is just the zeta 2 part, is then and there's a little Muddelstamms as entries, so I write just two guys as S1, 3, S2, 4, and S1, 2, S3, 4, and there are other things. So they're all degree of the same degree. It's a polynomial. And now I thought that you want to know what the single value is.
I think you can stop. I mean,
2 minutes?
2
minutes?
I mean, 2 minutes by 2 minutes.
But the 5 minutes are not yet over. So now this is very nice, and actually now we can get in the final 2 minutes we'll get a nice relation to the closed string amplitudes again. So we introduce a map which maps, which is the single value, which maps this algebra convolute to a subspace. So recall this map was spanned by this alphabet, a non-commutative space. So you have, for example, words like F3 and F5 and so on. And now, so how do we define this map? So we have a given word made out of this alphabet like F3 and F5, and this is mapped to this. Is mapped, so this is a shuffle product, which is just this guy times that guy plus this guy times that guy. So, and this means the reversion of the word. So what does it mean? Reversion of the word. So of course, if you just apply it for F3, then what can I do? F3 is f3 times 1, or it is 1 times f3. So that means f3 is mapped to SV of f3 is 2 times f3. Okay. Now what is remember this f3 times f4 was we can apply to a word which has 2, and then you can construct this. You get something else, no?
There is no F4.
Hmm?
There is no F4.
Yeah, no, F5, yeah. Yeah, you can now, for example, from this recall minus 4 times this was corresponding to zeta 3,5, so you can compute it. And then from here you can go back to the Motivic multi-zeta. So from here you see that F3 was the zeta 3 Motivic. So you see now that SV of zeta 3, or of the single element of this Motivic guy, is 2 times the ordinary zeta function. And if you do this, I mean, you can then, because there's a new map, and actually you can see that you can derive that the type 1 superstring couplings, if you think SV of that is the rotated superstring couplings.
I think we should have needed a few more lectures then, but thank you very much. We can take the
And you can ask me in
Thank you very much for your lectures. And we start 5 minutes after,
Okay.
so 25 to